So very good afternoon one and all. We are learning the subject of the electromagnetics. In the electromagnetics, we are taking the content and the topic of the wave propagation. Instead of wave polarization, we are going to continue the wave guides. Yesterday we have simplified many numericals on the basis of the polarization. Okay, but today we will continue the numerical on the wave guides. So you just keep ready your pen, paper and the calculator, cross verify the answer so that it will be easy to you. And for more practice, you just do one thing, uh, just change the value of numerical and try to do the practice at home. I am reading the numerical. All of you just pay attention and note down yourself and do yourself also. At least you just solve the numerical instead of writing the question. Read the question properly and then simplify the numerical with the help of the calci. Okay. So what is that numerical? All numerical are based on the wave guides. A hollow rectangular waveguide has a dimension of 6 centimeter into 4 centimeter. In the free space signals is of a 5 gigahertz. Calculate for the TE10 mode. Okay, already we have discussed the theoretical part related to the TE, TM and the mode of that is a 1001 whatever it is. Now the A part, what you need to calculate in the T10 mode, that is nothing but the cutoff wavelength, the phase constant, the wavelength, guide wavelength, and the D part is the intrinsic wave impedances. So these parameters you need to calculate in the waveguide. Okay, to remember which numerical is related to the waveguide, that easily you can understand with the help of the TEM mode or a TEM mode combination. Okay, either individual T or you can say the TM or TEM by combination of the electric as well as the magnetic field. In this way you can substitute the value. Okay, you can easily identify this is the numerical related to the waveguides. Even by understanding of the rectangular, circular, elliptical type, you can also identify if this is the waveguide numerical. Okay, now start with the first parameter that you need to calculate, that is nothing but cutoff wavelength. Okay, cutoff wavelength is nothing but at a particular frequency where resonance is occurring and critical or the cutoff frequency we are getting on that particular instant only we are interested in the wavelength. It's not a simple wavelength, entire wavelength is not there. It is a particular wavelength which is occurring at a critical frequency or the cutoff frequency where the resonance is occurring. Getting, and we know very well the condition where the resonance occurred and where we can find out that the critical or the cutoff frequency FC, F0 likewise. So here, what is the formula behind that? The lambda C is nothing but V0 divided by Fc. What is the V0? What is the V0? How you got this 2? Yes, any one of you can elaborate how we can say this is the 2. In the bottom, they mention clearly. Already we have seen in the rectangular A and the B, that is the width and the height, the value parameters, you can say parameters. A, B mentioned were mentioned in the rectangular figure of the rectangular waveguide. In that rectangular waveguide, we have seen the value of your A and the value of the B. Okay, and that A and the B, we how we can take in the form of the wavelength that is mentioned here. The lambda C is equals to 2 into A. And what is the value of the A? What is the value of your A? 6 centimeter. Convert this one into the meter also, or directly if you are taking the 12 centimeter, then later on convert into the meter. Okay, if you don't want to if directly if you want, if you at the beginning, if you don't want to take the value of the A, directly keep the lambda say like the 2. Okay, at present. Okay, at present. Later on you may change that one. Later on you may change that. What is the value of the FC? already we have this formula, m divided by a root of m divided by a whole square plus n divided by b whole square. What is this m and n? M and n is nothing but you are here mentioned. See here, 1 comma 0 mode. T is no doubt at all transfers of your the electric field, but especially 1 and the 0 what they mention here again, the transmission of your the what we can say number of modes where exactly it's going on. So that is mentioned in the form of your the m as well as the n. So that is mentioned m is 1, n is a 0. Similar to that, what are the parameters of your rectangular shape? That in other way you can say the height and the width, and at any you can consider that one, that is for your the AB. So that m n along with that you are the parameter, substitute this value, okay, and you just get. I hope you are getting this answer. That is, if you are going to substitute the value of your the m is 1 here, here is not mentioned, but you just take the 1 here, 1 divided by a at the beginning. If you're not taking, okay, but later on anyhow you need to take. Better way just take, because they what they are doing, instead of taking this b0 over at beginning, they are finding the lambda c. So 2 divided by l, 1 divided by c is nothing but my 0.06 in meter, 0 divided by 0.04 meter, substitute this one whole square bracket and the 2. So you will get as, here you just substitute the value of a also. So then only it is possible to get the value of your the lambda c. So you just tell, post me, any one of you just post me what you are getting the answer. So after getting this lambda c, you just substitute the value of your m 1, substitute the value of n 0, substitute the value of a is nothing but 0.06, substitute the value of b, that is a 0.04, okay, and 2 divided by root of all. So you will get the answer. Just post me, okay. Shashank, repeat the post. I am unable to see. So next is nothing but your the phase constant, that is denoted by your the beta, and the beta can be calculated as in this what we can say waveguide. Beta will be equals to root of, again in bracket, omega square mu epsilon minus in bracket pi by a bracket close of whole square. That is a derived expression. Okay, already we have done in the theoretical part. This is the derived expression. Directly you need to take this one while you are simplifying any kind of numerical. Now substitute the value. How it is possible to substitute? We know very well. This is angular velocity. Okay, angular frequency. Omega is nothing but angular frequency. Omega is equals to 2 pi f. Now you just substitute the value of 2 pi f whole square. We remember it's a whole square. Okay, so 2 square, pi square and the f square. Then later on you need to take, that is nothing but u and epsilon. Okay, that is nothing but again the pi by c. How you got this c square? Yes, how you got this c square? How you got this c square? C is nothing but, here what they taken, instead of writing the epsilon and the mu, directly they are taking as a 1 by root of mu epsilon. Have you remembered that formula of your the velocity of propagation, light velocity of propagation, that is 1 by mu of 1 by root of mu epsilon, directly you can take. So velocity, light velocity of propagation of light, you can take directly 3 into 10 raised to the power 8. So what we have altered here, just simply we have taken 3 into 10 raised to the power 8 of whole square minus pi by, what was there other thing, that is a pi by a was there na. So a value was mentioned 6 centimeter, converted into the meter 0.06, substitute here 1 by 0.06. So here 1 is not there, there is a pi, you just take the value of the pi and you just cross verify this answer whether you, even pi is taken outside also. See here, pi is taken outside, that is also possible. Okay, So either in this way, either in the bracket or on outside, you just take and cross verify with the help of the calci whether you are getting this answer 90.6 in converted into the radians per meter. Okay, radians per meter. This phase constant measured in the radians per meter. If you are getting the answer, all of you, I request you just post the answers. Third parameter we need to calculate, that is a guide wavelength, and that is denoted as your the notation lambda g, that is a guide wavelength, which is equals to 2 pi by beta, which is equals to 2 pi. Again here the beta value we have taken the same formula which we have taken in the above. So root of omega square mu epsilon minus pi by a square. So what will happen here? 2 pi will be as it is, and already we have calculated this omega square mu epsilon minus pi by a square. So substitute the value 90.67, 0.069 meters. Okay, so now the last parameter is nothing but your the intrinsic wave impedance. So intrinsic wave impedance can be denoted by the Z, and the Z is equals to, why we have taken here the minus? Yes, any one of you? Why we have taken here the minus? Here will be the plus or minus. For safer side, they are taken plus or minus because the H is in the X direction, Y is in the E is in the Y direction. H is the magnetic field. If we are assuming taking the reference as a H in the X direction, definitely my electric field will be in the Y direction. Okay, so in this way the ratio of your the electric as well as the magnetic field, both X and the Y, we have taken, and in the waveguide the electric field is taken as, while you are going to calculate the impedance, omega mu divided by the beta. Okay, so here this is the, you can say the ratio, while whenever you are taking the E and the H at the time for calculating the impedance, this formula is differ in the other wave, what you can say uniform plane wave and the wave propagation, but while you are going to calculate in the waveguide, so there will be somewhat difference. So here will be your the Z is equals to E by H is the ratio, we know very well. This is also the in the intrinsic of E by H. So here omega mu divided by beta, omega angular frequency 2 pi by F into, what is my mu, that we know very well, the constant value here. Instead of taking mu 0 mu r, if we are considering the air, then the one and constant value mu 0, that is nothing but 4 pi into 10 raised to the power minus 7. Already we have calculated the beta 90.6. Substitute the value, you will find as the intrinsic impedance is nothing but the 435 ohm. 435 ohm. 435 ohm. Take a next numerical. Previously was a hollow rectangular waveguide. Here also the rectangular waveguide has a dimension. See here the parameter, or you can say the dimension A and B is nothing but the dimensions, parameters of your the rectangular waveguide. Okay, A and B. 2 into 4.5 centimeter internally with propagated in it, with propagated in it find the characteristics. Find the characteristics wave impedance for the dominant mode. Find the characteristics wave impedance for dominant mode. So what is here? Rectangular waveguide has dimensions 2 into 4.5 centimeter internally. In this case, the what you can say the dimensions are mentioned. Okay, and what they are asking to calculate? They are asking to calculate the characteristics impedance. Okay, characteristics view impedance for the dominant wave. So dominant mode, in the dominant mode, in the rectangular waveguide is nothing but, we always remember, whenever you are having the type of your the rectangular, and definitely the dominant mode of your rectangular waveguide will be TE1, comma 0. That is TEMN, small mn. Here will be your mn. Okay, be remember. Here will be your mn, TEMN. M is my 1, n is my 0. Okay. The characteristics waveguide impedance for the TE is given as, see here the formula for finding out your the characteristics impedance of your the TE, that is 10, TE10, that is TEMN. Okay, so what is that? Already they have calculated the value of intrinsic impedance. We know very well this is the value of your intrinsic impedance eta. Either you may take the 377 or 120 pi. So that eta will be the root of e by h or other value mu by epsilon. Likewise, the constant values mu 0, epsilon 0. Likewise, you can get the 120 pi or the 377 instead of taking the e and the h. If you don't have that equations of your the e and h, at that moment you can consider your characteristics impedance either directly mentioned in the numerical, if not mentioned, with the help of the constant value, that is the mu and the epsilon, you can find that the value of intrinsic is a 120 pi or a 377. This will happen only and only whenever you are not having the characteristics impedance in the form of electric and the magnetic equations, or you can say the mu r and the epsilon r value. Material is not given, the medium is not given in that case only. So in the formula, actually here is the eta. ZTE is equals to eta divided by root of 1 minus lambda 0 lambda c. Lambda 0 is nothing but you are the wavelength of your the free space. Okay, wavelength of your the free space. We remember in the many of the textbook they are also referring this 0, and that 0 is treating as a free space, and c is nothing but the cutoff. At cutoff or the critical. Okay, cutoff or the critical notation is given. Fine. So in this way you can calculate. For the free space wavelength lambda 0 is nothing but V0 by F. What is the V0? Velocity of wave propagation of your the light. Divided by F is nothing but the normal frequency. Okay. Is there any frequency is given? If not given, you can assume for the rectangular waveguide the normal frequency will be over the 9 gigahertz. We remember for the waveguide normal frequency range will be over the 9 gigahertz. So here, just like you are the reference of your the light at that particular light velocity of your the light, you can consider your the frequency will be over the 9 gigahertz for the waveguides. So you just substitute the value of your the V0 and the F, you will get as 3.33 centimeter. You may convert into the meter because the wavelength measured in the meter. Okay, so 3.33 is in the centimeter. Similarly, the cutoff wavelength, that is a lambda c at a mode 1 and 0. So lambda c is equals to 2 into a, so 2 into 4.5 is mentioned in the numerical. The frequency is also given, no doubt at all. If not given, take the what we can say other value here. What they given 9 gigahertz. 9 into 10 to the power 9 is given. So in this case, lambda c can be calculated as, how you can find out the lambda, how you can find your the lambda c, 1 and 0, 2 into 8, 2 into 4.5, that will be 9 centimeter. Okay, so in this way z characteristics impedance for the TE, that is a transverse electric field. So eta value is 120 pi divided by 1 minus just substitute the value, it will be able to find as 120 divided by 0.93 of root calculation, you will find 405 ohm. I hope you are getting the answer. If you are cross verifying with the calculator, go for the third numerical. What is that one? Third numerical. Find find at find at what transmission mode find at what transmission mode in bracket TE and TM are possible. TE and TM are possible at an operating frequency of 3 gigahertz in the hollow rectangular waveguide of a dimensions inner dimensions A part 6 centimeter into 4 centimeter, 6 centimeter into 4 centimeter, B part 3.44 centimeter into 7.22 centimeter at 2.5 gigahertz. Second, find also corresponding value of your the phase constant. Find corresponding value of your phase constant, comma phase velocity and group velocity and group velocity. So what they mention in this numerical, two things are mentioned. We need to find the transmission mode, that is in the TE and the TM. They given the operating frequency along with your the dimensions. Second case, we need to find the phase constant, phase velocity and group velocity. Very interesting numerical is this one because you need to find out many parameters. Getting? So let's start here. So I think this is an incomplete numerical. So instead of this one, we just take this one because this is an incomplete numerical. So I will continue this one and we will see later on the previous because that is incomplete numerical. Previous one, all of you note on this numerical first. All of you continue this numerical. An air-filled hollow rectangular waveguide. An air-filled hollow rectangular waveguide has a dimension of 8 into 10 centimeter. 8 into 10 centimeter. How many TE modes? How many TE modes will this waveguide transmit? Will this waveguide transmit at frequency below? At frequency below. At frequency below 4 gigahertz. 4 gigahertz. Stuff. How these modes are designated? How these modes are designated and what are their cutoff frequency? And what are their cutoff frequency? So in this what they mention here, this is again the rectangular waveguide is there and dimensions are 8 and the 10 centimeter. So how many TE modes will this? Okay, so TE modes are important here. TE mode will this waveguide transmit at a frequency of 4 gigahertz. We need to calculate how these modes are designated and what their the cutoff frequencies mentioned here. So see how we can simplify this numerical in all the cases. That is here M and N are important because we know very well in the either the TE or the TM, TE M comma N, TM M comma N. So M and N gives the mode. Okay. mode of operation, you can say, in the transverse electric field, in the transverse magnetic field, in the both the cases. So here we need to focus on the modes. What will be the cutoff frequency for every modes? So how we can start? It is given that maximum frequency of your the waveguide can be transmit is of 4 gigahertz, is mentioned clearly in the numerical. Secondly, for the minimum wavelength, for the minimum wavelength, lambda c v0 by f. So what is v0? Velocity of light is nothing but 3 into 10 to the power 8, and here the frequency is mentioned, that is again the 4 gigahertz is mentioned. See here. So just simplify this one, you will get 0.075 in the meters. Convert into the meters, already so converted, that is 0.075 meters. Now the cutoff wavelength lambda c is given by, now calculate the lambda c by considering the dimensions, by considering the modes. So what is the, where is that modes and the dimensions? The mode and the dimensions are 2 divided by root of m by a. So 2 divided by root of m by a whole square, n by b whole square, where a and b are in the centimeters, take as a centimeter, and we are interested here m and n unknown parameter we need to calculate. So this will be the final of your the 0.8 root of 16 m square plus 8 n square in the meters. So lambda c for the m is equals to 1, n is equals to 0. So what will happen? So what are the possibilities here? The 1 0 0 1 1 1 2002. So for up to this limit we are interested to find out later on the case, but we are interested at present this one only, 1001. See here, 1001, again 11. See here, huh? Instead of taking 00, we are not taking a 00 part here. 100111 2002 2002 likewise. So in all cases, substitute the m, substitute the 00, then the 11, then the 12, then the 00, then the 2. Likewise, you can calculate the lambda c with like 0.2 meters, 0.16 meters, 0.12 meters, 0.1 meter, and 0.08 meter by substituting the value in this formula. Okay. So see here in the next also, they what they mention. So see here in the above 2 0, no? Then the 2 1, then the 1 2. See here 2 1, then the 1 2. So likewise 0.0087 meter, 0.073 meter. So we have calculated all the how many 7 lambda c cutoff frequency in all modes. So we remember the modes which we are taking 0 1 1 0 1 1, then the 2 0 0 2, then the 2 1 1 2 likewise. Okay, so these we need to take. Only these modes for which the lambda c, whether the lambda c is greater than the lambda 0, will be propagated. So only the first 6 modes are propagated. See here how we are comparing whether my cutoff wavelength is greater than the wavelength at the free space. Okay, so this we are getting the comparison whenever the if lambda c, that is nothing but cutoff frequency, at a cutoff frequency the wavelength is becomes less than the free space wavelength, then that time no need to consider, because the propagation will happen whenever the lambda c will be greater than the lambda 0. So the modes are will be designated 1001, 112002, and 21 instead of 21. Okay, not the 12, 21. See here, so the cutoff frequencies are FC for the TE10 will be again the cutoff frequency. Again, second question is nothing but the cutoff frequency, V0 divided by lambda c. Substitute the lambda c everywhere. Substitute the lambda c everywhere. Okay, at the beginning. Now for all mode 1, 2, 3, 4, 5, 6. Okay, up to the 6 only. 1001 11 2002 21. So here previously we have calculated the lambda c, and okay, the and with the help of lambda c we have calculated m and n. all modes, what will be the lambda c? Now come toward the point. By considering that same lambda c, now find out the cutoff frequency. So cutoff frequency for so and so mode by considering this lambda c will be your 1500 hertz. Secondly, the lambda c is this one, mode is this one. Two things are important here, lambda c as well as the mode. These two we are focusing. By considering these two, we are interested to calculate the fc. So 1875 hertz. Similarly, this mode and this lambda c. Consider these two, find out the fc. Consider these to find out the fc. Consider these to find out the fc. Similar to that, consider this to find out. In this way, we have calculated the lambda c, modes, and the cutoff frequency. Go for the next numerical. What will be the cutoff wavelength for the dominant mode in the rectangular waveguide whose breadth is 15 centimeter for the 2.5 gigahertz signal propagated in the waveguides in the dominant mode? Calculate the wavelength and the group phase velocity and the characteristics wave impedances. So we know very well the dominant mode will be the TA, that to 10. So cutoff frequency, cutoff wavelength will be lambda c 2a divided by m. 2a will be so that will be equal, because the m is treated as a 1 here. This is m and n. M is 1, n is 0. M is 1 and 0. So 2a, this will be equals to 2 into 15, 30 centimeter is the cutoff wavelength. Similarly, the guide wavelength is nothing but lambda g. Lambda g is nothing but lambda 0 divided by 1 minus lambda 0 square divided by lambda c, root of this one. If you are taking root 1, take 1 by 2, lambda cutoff frequency and the frequency, the free space wavelength. So these two are wavelength. Find out the free space wavelength, and lambda 0 p0 by f. So 3 into 10 to the power, and the f is given 2.5 gigahertz. So 2.5 gigahertz, find out into the meter, convert this one into the meter. Lambda g, by substituting this value, you will get as 13.09 centimeter. 13 centimeter. Now next parameter will be the phase velocity. Vg is equals to omega by beta. Omega is nothing but v0 divided by root of 1 minus lambda 0 divided by lambda c whole square. Substitute the value of v0 light and the whatever you have calculated this beta, that is a 0.91 in the above slide we have seen. So after calculating these two, the numerator and denominator, you will get this value in the meter per second. Group velocity is nothing but Vg of a gr, v0 1 minus. These are derived formulas, so keep it as it is. Either you can take in the root or you can take in the 1 by 2. So lambda square, lambda c square. So 3 into 10 to the power 8, 0.91 and 2.73 and 10 to the power 8 meter per second. So will be the case. And last of wave impedance, that is equals to omega mu by beta. You have 2 pi f angular velocity, and the mu will be as it is, that is a constant 4 pi 10 to the power 7 minus 7. And v0, you can convert this omega mu 0 likewise. Okay, likewise you can convert this term, you can convert likewise. If they are this is substitute the value, you will get the answer 414.2 ohm of your the impedances. So in this way, we have completed 5 numerical on the waveguides for the today's session. Okay. So in the next lecture, we will continue the rest of the numerical. Till that period, thank you so much.